Good morning, I'm Giulia De Lucia and we present the work Geometric and Structural Information for the Analysis of Historical Domes, the case of the Santissima Trinita Church in Torino. This study was conducted at the Dynamics and Earthquake Lab, coordinated by Professor Rosario Ceravolo at the Politecnico di Torino. The main scope of this research is to highlight the relevance of geometric and historical information for structural analysis, but also to demonstrate the possibility to improve historical research through structural and analysis results. Before that, let me show an outline of the presentation. First, I will present a brief introduction of the case study. Then, geometric and structural investigation conducted through the numerical model of the structure will be presented. Principally, this analysis deals with some structural depressions of the masonry detected on the internal surface of the dome. Then I will discuss the results and conclusion. The case study is the Santissima Trinita Church, an important church for political, artistic and religious story of the city. Indeed, the church is located in the center of Turin, very close to the royal palace and to the Duomo, so a very strategic position. At the end of the 16th century, the Santissima Trinita confraternity was very popular and wealthy, so much they obtained the soil in the center of the city. Then, the confraternity requested the ducal architect Ascanio Vitozzi to design and build the church. He designed a circular central plain church with the coif behind the monumental altar. The construction began in 1598. In the same years, Vitozzi was working on the impressive project of the Sanctuary of Vicoforte. Therefore, in the same time, he was designed two important domes. One will become the world's largest oval dome, and the other was the first one-shell dome built in Turin until that time, because the previous ones were segmented domes. However, Vitozzi died in 1615, and both the construction were not completed. So, these domes were posthumously terminated. The Santissima Trinita dome was completed in 1661, but we don't have information about the architect who completed the work, or if the original Vitozzi's project was respected, because all the worksite documents were destroyed in the fire caused by the 1941 bombardments. For this reason, the paternity of the dome is an important historiographic node to be solved. Between 2016 and 2020, with restoration works, new study and structural analysis on the building were conducted. Our first consideration were geometric investigations, because Vitozzi designed the church on geometric and symbolic basis, related to the number 3 due to the Holy Trinity. The project was very refined in terms of geometric proportion. As you may observe, the basement of the church has the same height of the dome, and a similar relation is between the lantern and the little lantern. The drum and the base of the lantern are the half of the internal diameter of the dome, and the thick of wall at the base of the dome is the third part of the altar. These proportions confirmed design traditions in sacred architecture of 16th century. Geometric studies on the section of the dome demonstrate that the dome, that seems to be elliptical, is designed starting from a 4-point oval arc. During the recent restoration works, a laser scanner survey of the intrados of the dome was performed. Then, the scans were elaborated as a point cloud. Given access to this point cloud, allowed the current shape of the dome to be investigated. The point cloud was transformed into a mesh. The mesh showed several irregularities and depressions on the intrados of the dome. They are especially located on the northern side of the dome, to the right of the main altar. For convenience sake, the dome was subdivided in 4 dials, starting from the main altar in a clockwise direction. In this scheme, the main depressions are located in the first dial. The discrepancies reach values of 19 cm in some areas, such as in the first and in the third dials. You may observe also some problems at the impost of the lantern. In order to investigate the structural behavior of the dome drum system, structural analysis on a numerical model had to be carried out. Two different solid element models were used, both built with a macro-modeling approach and the Diana code. The first model is an elastic linear model representing an idealized configuration of the dome, without defects or deformations, model I. The shape of the dome was created with a simple revolution solid of the profile section obtained from the archive drawing. Then the model was completed with the drum and the lantern. The second model reproduced the current configuration of the dome as resulting from the survey and called Model R. This model was created by using directly the geometric information obtained from the scans. For what concerns the material characterization, data from literature were used in the lack of in situ experimental investigation. The parameters of the linear model I were taken from a study conducted on the material characterization of the masonry of a building in Torino, almost contemporary to this case study. For the non-linear model R, a standard elastoplastic model based on the Drager-Prager criterion was used, considering the masonry as a material with isotropic behavior and plastic deformations. Even in this case, data about the elastic phase and the resistance of the masonry were taken from literature. Then, vertical loads and snow loads were applied to the dome, in addition to the punctual loads related to the two roofs placed on the extradus of the dome. Both models were constrained at the base of the tambour, assuming the rest of the building as very stiff. Static analyses were conducted with the aim of obtaining information about the global structural behavior of the dome drum system, and in order to investigate the possible causes of the appearance of the depressions and their influence on the structural state of the building. In fact, the depressions could be due to the construction defects and imperfections, to structural problems which appeared over time, or to the fire experienced by the dome in 1942. In this perspective, static analysis conducted on a basic model can be useful in a preliminary stage to shed some light on the stress distribution and to displacement affecting the dome, although the assumption of an elastic behavior for the masonry does not correspond to its real behavior. According to both models, the stress state due to the constant vertical loads is moderate. Instead, for what concerns the displacement distribution, we may observe two different results between model R and model I. In fact, model R has not uniform distribution along parallels due to eccentricity of the lantern. In particular, higher displacement can be observed at the base of the lantern in the third dial, exactly on the opposite side to the area with the main deformation, to which the eccentricity of the lantern seems to be correspond. The effect of this eccentricity is a compression increment at the base of the dome, on the third dial, and a decompression increment on the fifth dial. The decompression results in a greater inflection values on the first dial area measured at the same height level, in particular on the area affected by the large deformation. In order to investigate and deep the displacement trends by analyzing both the internal and external surface of the dome, 5 reference heights were defined, each of which had a relevant increment of displacement value. Then, the vertical displacement and stress values on the nodes located at the intradus and extradus of the dome were obtained. In the area between 17 and 21 meters, measured from the impost of the drum, the displacement values for both intradus and extradus increase with the increasing height. As far as the vertical stress is concerned, the values measured on the extradus follow the same trend, while in contrast they decrease on the intradus. At this point, creep analyses were conducted in order to investigate whether a possible cause of the depression observed around the dome can be related to the viscous long-term behavior of the masonry. The method used for plotting long-term displacement curves was taken from literature, assuming the mortar be the viscous phase of the masonry material. Data on the mortar came from constant compression tests reported in literature. You may observe the evolution over time of the vertical displacement values. The model confirms the first year of the dome to be more affected by viscous phenomena in accordance with the observation. So, the vertical displacement values were plotted as a function of time, extending the creep analysis to a period of 400 years, approximately the age of the dome, to have a qualitative evaluation awaiting more in-depth investigations, also due to the lack of accurate data on materials. In conclusion, the FAME model confirms that geometrical deformations observed on the dome are not alarming for the current structural health state of the building. Moreover, it was observed that the viscous deformations, possibly due to the construction defects and imperfections, can have an important influence on the stress and deformation state of the dome. In this specific case, the numerical models showed that the observed leaning of the lantern system, as evidenced by the digital survey, can be the cause of depression on a side of the dome and the consequent depressions in the intrados. The results can still support some qualitative but useful structural engineering evaluation. It might as well help historians finally resolve the controversy on paternity of this dome, which has long been committed in the scientific community. Future studies will address the influence of the fire caused by the World War II events.